Hello and welcome back to our concepts of probability. In this next section, we will be looking at some actual statistical analyses and running through those in a systematic way. As a quick review, we have a sample drawn with a mean of 185, and we are testing the null hypothesis that the mean of the population that it was drawn from is equal to 170. So here's our picture of that. We've calculated our standard error, we know the mean, we have our sampling distribution, we have our 95% confidence of the X bars. So here we have our statistical analysis that goes along with that particular question. So our null hypothesis is that the mean is equal to 170. We're doing a two-tailed test, and so our alternate hypothesis will be that the mean is not equal to 170. The statistical test that we will run, I haven't told you this yet, I was keeping it from you. The test is a one sample z-test. And the assumption for that is normality. So that particular test only has one assumption, and you learned that it's normality of the distribution or of the sampling distribution of the means. And so we achieve that either by having a sample size of 30 or more or having the underlying population be normally distributed. Our test statistic is worth looking at here. So our test statistic is equal to z, and we graphed z over here. The z values are right here, so we could kind of see them. If you were to correlate a z value with 185, you would probably say that that z value is equal to 3, and you're correct. The thing I want to show you is how that z value is calculated. And I know a lot of people get really anxious when we start delving into the equations, and so that's exactly why I drew the picture for you first, because I think intuitively you know that an x bar of 185 is equal to a z value of 3 because you saw it here. You could see that how that kind of plays out. Let me show you how that calculates out with numbers. So here we have our z, that is equal to x bar minus mu divided by sigma over the square root of n. So these are all values that are your friends by now. X bar is equal to 185, mu is equal to 170, sigma over n over the square root of n is equal to 5. So let's go ahead and do that. 185 minus 170 divided by 5. And that gets you 15 over 5, 5, which is equal to 3. So there's the handy little 3 that we actually already came up with. So the test statistic isn't so scary after all. Now, what we need to do, so that was steps 1 and 2, is to state our null hypothesis and figure out what our test is going to be. The third part of that is to actually make a decision, and that's a decision about what we want our critical value to be. And by critical value, what I mean is the p-value above which we will fail to reject the null and below which we will reject the null. By standard convention, the critical value, because we have this 95% confidence, or the 1 out of 20, is anything above or below 0.05. If you use something different than that, it's fine. You would probably need to sort of explain why you wanted to use some other number than that, but it's okay. There's not something magical about the 0.05, so feel free to use something else. When we calculate the p-values, then we're going to compare the calculated to that critical value and decide either reject the null or fail to reject the null. And remember, we're always testing, remember how we're always testing the null hypothesis. We're not testing the alternate hypothesis. That's usually our research question, the alternate. We're testing the null hypothesis. And we already learned just from the graph that the p-value that goes along with this z value of 3 is 0.027. Now, The computer will always calculate that p-value for you, but what you need to remember is the smaller and smaller and smaller and smaller that p-value gets, the less and less and less and less likely this null hypothesis is to be true. That means that you're getting farther and farther and farther and farther away from this proposed value of 170. And this p-value goes from 1 to 0.32 to 0.05 to 0.27 to 0.00007, and it just keeps getting smaller and smaller the farther away you get. So the bigger the difference between our test value, our sample value and our test value, 185 and 170, the more likely it is that you will say, no, I do not believe this null hypothesis is true. And so whatever critical value you decide on, if this number is less, that means that you reject the null hypothesis. If it is more, that means you fail to reject, and I use FTR, the null, just for abbreviation because I don't want to spend all day writing it out. So reject or fail to reject the null hypothesis. And in this case, it is less. 0.027 is less than 0.05. So I'm going to say reject the null. And what that means in plain language is that it is very unlikely to draw a sample with a sample mean of 185 to have been randomly drawn from a population with a mu equal to 170. In other words, less than 2.7% of the time would we randomly draw this sample right here from that particular population. So the conclusion is something that a lot of times we write in kind of APA format, American Psychology Association, and you'll see a lot of times this very condensed format. So this is 1, 2, 3, and 4. This is kind of like our process that we go through. Based on all 4 of those, then we can draw this conclusion, or step number 5. The average weight of participants, M stands for mean, of 185, standard error equals 5, was significantly greater than 170, our proposed value of 170. We write our z-value, the degrees of freedom, which is just simply n minus 1, and our p-value that goes along with that. That's just as condensed as can be. When people are looking at a conclusion, that's exactly what they're looking for. They're searching for all of these particular elements to be in that specific location. Now, if we find it to be statistically significantly different, we can say what direction that is going. We can say if it's greater than or less than, even though our 95% confidence interval here really doesn't tell us anything about direction. Remember, it was the absolute value of that z-value, or more extreme. So we can still say that in our conclusion, even though we did not do a one-tailed test. A lot of people will ask about that. So this is a two-tailed test, and that's how we would run that particular test for this question of 170. If we have a sample with a mean of 1, oh, my screen seems to be freezing up. Okay, there we go. Didn't mean to scare you. Okay, so the next thing that I would like to do is I would like to say, okay, well, let's imagine instead of having a mean of 185, let's say that just this particular example, we drew a sample with a mean of 173, and so I'm going to draw that mean here. It would have, we would have our middle of that sample would be about here, and it would kind of go a little bit more like that. So what are the chances that if this null hypothesis is true of 170, that we drew a sample that has a mean of 173? And if you just intuitively look at that, if you look at the location of this sampling distribution of the x bars of the sample means, you can see that this falls very nicely in the bulk of where a lot of these x bars will be, whereas this one kind of was way out here in the tail. So hopefully intuitively you would say kind of the answer to that question. Would you be surprised about that? You would say, no, that seems like it could happen because this seems pretty close to the 170. The 173 doesn't seem like it's that far away. So let's go through that exact same example. We'll keep our sample size the same, and let's fill in this particular statistical analysis. So our null hypothesis stays the same. It is the mean is equal to 170. The alternate hypothesis is that the mean is not equal to 170. The test is a one sample z-test. The assumption is normality. So far, exactly the same as what we did before. Here's where the difference is going to lie. And this is where we have our z-statistic. And again, it's x bar minus mu divided by sigma over square root of n. Instead of having 185 minus 170, now we have 173 minus 170 divided by 5. In other words, we have 3 over 5, which is equal to 0.6. And if we look back here at our table, we would kind of follow this down and say, yeah, that does look like a z-value of about 0.6. If 175 is a z-value of 1, of plus 1, and 170 is a z-value of 0, then 173 would be a z-value of 0.06, or sorry, 0.6. If we keep our critical value the same of 0.05, if you looked on a table, you could find this. The p-value, this p-value that's actually calculated for a z-statistic of 0.6 is equal to 0.55. Now remember, the p-value is, if the null hypothesis is true, then what is the probability? What are the chances that we will get a z-value of 0.6 or one that is more extreme? And what this tells us is that we have a 55% chance of drawing that. That's pretty likely that we're going to draw a sample that has an x-bar around 173. Now, if you think about this 173, 173 does not equal 170. That's not the question that we're asking. We're asking if 173 is statistically significantly different than 170. Not whether it's different, but whether it's statistically significantly different. So in this case, 0.55 is greater than 0.05, and so we fail to reject the null. We say, yeah, sure, I could go with that. That seems reasonable. In plain language, it is quite possible for a sample with a sample mean of 173 to have been randomly drawn from a population with a population mean of 170. So we think, yeah, that could happen. That's pretty likely. And the way we would write that conclusion then is the average weight of participants, mean 173, standard error of 5, was not significantly different than 170. Z of 0.6, degrees of freedom stays the same, and our p-value is 0.55. So that is, in a nutshell, running a statistical analysis, one where we reject the null, one where we fail to reject the null, and you kind of see that process as we go through. In summary, I want to encourage you, test statistics are not scary. Not all of them are as easy to do as this one was, kind of by hand. We actually just plugged the numbers in and calculated them. But it all goes back to the underlying concept. And so if you can understand that underlying concept, then those equations don't need to be a frightening or a scary thing.